Use this PES for sulfur, and note the energy is increasing from left to right, the binding energy. Write the complete electron configuration and label the PES. Which peak corresponds to sulfur's valence electrons? Would the same peak in chlorine be expected to have a higher or lower binding energy compared to sulfur? Compare the radial size of the sulfide ion to its parent atom, and does this spectrum support the Bohr model of the atom? Consult the periodic table and find out that sulfur has 6, 12, 14, 16 electrons, and map it out 1s2, 2s2, 2p6, 3s2, 3p4. And that goes right over there. Okay, that subshell goes right to the right because that has the greatest bonding energy. You need the most energy to take away those 1s2 electrons. And then you move over to 2s2, 2p6, and also note here the height of this is equivalent to here, so we're going to say that's 2 electrons. Then 2p6, this peak is 3 times the height of this one, and that makes sense. 3 times 2 is 6 electrons. 3s2 on a par with 2s2 and 1s2, and finally 3p4, and this is double the size of the 3s2, double the intensity. Which peak corresponds to sulfur's valence electrons? Well, that would be over here. The binding energy of 1.0 corresponds to sulfur's valence electrons because it's the smallest. Valence electrons have the least binding energy, and sulfur's 3p4 is its outermost subshell having the lowest binding energy. Would the same peaks in chlorine be expected to have a higher or lower binding energy compared to sulfur? Well, the same peak in chlorine, right, whether it's the 2p6 or the 2s2, will have a higher binding energy compared to sulfur, as it has a higher nuclear charge due to its extra proton. Chlorine has 17 protons and sulfur has 16. With a greater attractive force between electrons and protons, it will take more energy to remove electrons from their subshells. Compare the radial size of the sulfide ion to its parent atom. Well, a sulfide ion is S2-. That means the ion has 3 more electrons than sulfur. The sulfide ion's electrons experience a greater electron-electron repulsion, so the radius of the ion increases. Does this spectrum support the Bohr model of the atom? It does not. Bohr's model predicted individual shells, right, n equals 1, 2, 3, 4, etc., but not that of the subshells. So Bohr's model would predict 3 shells or 3 peaks in the PES spectrum. The actual spectrum has 5 peaks, 1, 2, 3, 4, 5, representing the 1s, 2s, 2p, 3s, and 3p subshells that exist.